In a world brimming with unstructured data, modern artificial intelligence demands tools that transform chaos into comprehension. Among these tools, the vector database is emerging at the forefront. What is a vector database, and why has it become central to the new era of AI? Today, we journey through the core of this technology, tracing its role in powering intelligent systems. To understand vector databases, start with the vector itself. In machine learning, a vector is simply an array, a sequence of numbers representing features, concepts, or context. This is the format most data becomes after being processed by AI models, whether it describes images, words, audio, or even user behavior. Traditional databases, think of relational tables or document stores, are optimized for searching and retrieving structured information. They work efficiently when looking up exact values, but stumble when searching by similarity, which is essential in many AI applications. Here, the vector database enters the scene. A vector database is engineered specifically to manage, store, and search billions of vector embeddings. These embeddings are high-dimensional representations computed by neural networks, capturing meaning and relationships between data points far beyond what conventional keys and indexes can express. Consider how you might search a library using keywords versus describing the theme of a book. Vector databases enable this thematic, semantic search. They answer questions like, "Find me items similar to this," even when no explicit tags or keywords match, a staggering leap from keyword search. Let's take a familiar example: recommendation systems. When a person shops online, an AI can compute a vector for each product and for user behavior. Finding similar items or predicting preferences is, in essence, a matter of searching for nearby vectors. Without vector databases, this process is painfully slow and inefficient at scale. Vector similarity search, the beating heart of vector databases, measures how close or similar two vectors are in their multidimensional space. Common distance metrics like cosine similarity or Euclidean distance translate mathematical proximity into semantic relevance, foundational to tasks like image recognition and natural language understanding. What does this look like in practice? Imagine an app that lets users find images of dogs similar to a given photo. An AI model encodes each image as a vector. The database stores these vectors, and when a new image is input, the app finds the most similar vectors, surfacing visually akin images, all in milliseconds. Scale is a defining challenge. Production AI systems may compare a single query against millions or even billions of vectors. Storing, updating, and efficiently retrieving from such vast datasets is exactly where vector databases shine, thanks to specialized indexing and distributed architectures. Let's talk architecture. Vector databases are typically decentralized, supporting horizontal scaling, adding nodes as data grows. They exploit memory and disk for efficient vector storage, but also provide advanced strategies like sharding and replication to maximize throughput and resilience. Indexes are crucial for performance. While traditional indexes support lookups by exact keys, vector indexes are designed for approximate nearest neighbor, ANN, searches. Algorithms like HNSW, IVF, and PQ enable these rapid similarity matches, trading off minimal recall for massive speed gains. HNSW, or hierarchical navigable small worlds, is one cutting-edge technique. It builds layer graphs where vectors connect to a handful of close neighbors. Searches traverse these connections, quickly narrowing down to the most relevant vectors, all while keeping computational costs low. Other techniques include inverted file indexes, or IVF, which partition the vector space into clusters. Queries navigate directly to the closest clusters instead of exhaustively searching the whole space, making searches dramatically faster on large datasets. Product quantization, or PQ, is another innovation. It represents vectors using compressed codes instead of raw values, shrinking storage requirements while still preserving enough information for effective similarity search. This method enables scale not just in speed, but in economical use of resources. How are vectors generated? Most commonly, vectors are outputs from deep neural networks like transformers or convolutional networks. Texts, images, audio, and even video can all be encoded into dense, multidimensional vectors, each dimension capturing nuances of meaning or appearance. The process typically begins with raw data. Take sentences, for instance. A language model transforms them into vectors. Each vector groups together similar meanings, so paraphrases cluster closely, while contrasting ideas sit further apart. This clustering underpins a new standard in search and recommendation quality. Real-time applications drive further demand for vector databases. Whether for chatbot retrieval, malware detection, or real-time personalization, results must be instantaneous. The power of the vector database lies in delivering relevancy at scale, in milliseconds, with zero tolerance for lag. Let's zoom into hybrid search, a key innovation. Hybrid search combines traditional keyword techniques with vector-based similarity. This synergy means apps can filter by attributes, like tags or dates, then rank results by semantic closeness. The outcome is high-precision, context-aware search that feels intuitive. Popular vector databases include Milvus, Pinecone, Weaviate, and FISS. Each offers different strengths, such as integration with machine learning pipelines, distributed deployment, or pluggable indexing modules optimized for unique workloads. Choosing the right one depends on use case, scale, and operational priorities. How do vector databases power generative AI? Consider Retrieval Augmented Generation, or RAG. Before answering a complex question, a large language model retrieves relevant background content using vector search. Fused with topical context, the model's output becomes dramatically more accurate and trustworthy. Security is non-negotiable, as sensitive personal and enterprise data is increasingly vectorized. Vector databases must implement robust controls. Encryption, multi-tenancy, and fine-grained access permissions become as critical as performance and accuracy in enterprise scenarios.